And we can begin with the lecture. Sorry for the delay. The internet was a bit buggy and I wanted to fix this. All right, where's the participant list? Okay. Let me monitor the chat. There we go. All right, glad to see you all back. Welcome to week number 7. This is progressing fast. And so remember last time what we had was the composition of transformations. So that was what we spent the last hour last week. And I'm going to start these week's lectures. You can see that this is the first slide without a heading, but the heading will be on the second slide. I just want to recall a few things about the composition, do one discussion, and then we'll move on to this week's first topic, which is the inverses of transformations. I don't know if we can cover all of these things. Change of basis we'll definitely do tomorrow, but the determinant, I don't know how far we will get this week. But that's the game plan for this week. Okay, so first of all, let me remind you what we ended up with. If we have two transformations and the domain of the second transformation is the codomain of the first one. So this means it makes sense to whatever the first transformation spits out in V can be then plugged into T so that we can apply T to the result of S of U. Then we say that these are composable. It makes sense to talk about the composition. And in this case, the proposition that we ended up with last time was that the composition has, of course, a matrix that represents this transformation. And this matrix is given by the product of matrices of representing S and T separately. So whether you compose transformations, T composed S on the left-hand side, and then take its matrix representing it in bases alpha and gamma of U and W, or whether you compute the matrices of T and S first, and then you compose those in terms of matrix multiplication, that's is absolutely the same. So just to make this clear, if you have U from V to W, the composition of S and T is T composed S, going from E to W. And that leads me right to the first discussion. If there are no questions, do you have any questions? So I think this is a very nice example to see how this works. These two sides of first composing and then taking the matrix, or first taking the matrices and then composing. I'll give you a few minutes to think about this. So we've seen before that if you have a polynomial and you have the linear transformation, which is given by taking the derivative, then in the standard basis of monomials 1x and x squared, this transformation, which is linear, has this matrix as a representation. And now if you apply the above statement, you should verify that if you compose this with itself, so if you do d by dx and then you compose this with d by dx, this will be another transformation going from polynomials to polynomials. And I want you to verify what the matrix of this is. All right. Can someone tell me what they think about this discussion? If you have any comments or questions. I mean, you can start by commenting on how this fits into the statement above. So this matrix here, I didn't write this explicitly in the slides, but this d by dx in the matrices and the bases alpha alpha is equal to this a. And when we compute d by dx composed with itself, so this is literally taking a derivative of a polynomial and then taking derivative again, then this is equal to the second derivative. This is just what the second derivative is supposed to be. And then we can verify that. So first of all, the easy side is when we just multiply matrices. It just means that when we take d by dx, the matrix representing the derivative, and then we do this again, then we have two matrices and we can multiply them. So this is just a times a. So this is a squared. This would be the matrix product of 0, 1, 0, 0, 0, 2, 0, 0, 0 with itself. So we have again 0, 1, 0, 0, 0, 2, 0, 0, 0. And if we compare the way that we did matrix multiplication, I introduced it last week, was we take the columns of the second matrix of the second factor, the rightmost factor, and we take the rows of the first factor. And then the ij entry in the resulting matrix will be the dot product of the ith row in the first matrix times the second times the jth column in the second matrix. Yes, so Andrew wrote in the chat the matrix, and that's correct. And you can verify this is the result because whenever any of these columns, so the first column is completely 0. This means that when you multiply this column with any of the rows, you get 0. Hence, these entries have to be all 0. The second one has only one non-zero entry, but if you pair this second column with the first row, this one goes to the 0 and then there's 0. So there's also no non-zero entry in the second column. And the only pairing between one of these three columns and these three rows is this column with this row. And so the reason that we have this 2 here is this last column with this first row. Everything else is 0. And okay, so we've seen that this is let me call this the left-hand side. So this is the left-hand side. Sorry, no, this is the right-hand side. So the right-hand side here is the product of the matrices of two transformations. And now what we need to verify is what is the matrix of the composition. So now we need to compute the left-hand side. For that, let me shrink this down a little bit. So this was the right-hand side. And to do the left-hand side, we need to find the matrix of d by dx squared. So we need to find, should switch to the size, d by dx squared from alpha to alpha. But remember, how did we do this again? We just applied the operator, the transformation to each element in the basis, and then we wrote this as columns. So now we need to apply the algorithm. By the end of the lecture, there will be a second algorithm, so I can no longer refer to the one algorithm that I included in the lecture. This means this is going to be a matrix with 3 columns. The first column, so there will be 3 columns. The first one is just going to be d by dx squared applied to the first basis element. Remember the 3 columns, one for each element in the basis. So this is 1x and x squared. This is going to be 0 because it's a constant, and hence the column vector representing 0 in alpha is just 0, 0, 0. So this is the first column in this matrix. This is 0, 0, 0. Second one is the second derivative of the second basis element, which is x. This is also 0. So again, the coordinate vector of the 0 polynomial is 0. So the second one is also completely 0. And then last but not least, we get something interesting, because if we take the second derivative of x squared, this will be one derivative applied, which is 2x. And then again, we get just 2. And in the basis alpha, which is just basis polynomials, this corresponds to the tuple 2, 0, 0. So this is our last column in this matrix. So we get, in fact, 0, 2, 0, 0. And then we verify that indeed the left and the right-hand side actually agree. I wonder whether I could write this somewhere. So the upshot of this is that left-hand side is equal to right-hand side. And this is the explicit example of the statement above, the proposition from last week. Can't believe it's already almost 3:30. We haven't even started with the content from today. But let me still ask for questions, because that's important. Anything that you would like to clarify? So I see it in the chat, there's some discussion about the order of the basis. You can do it in either order, but if you start with the one order, you have to keep it. And this matrix here, this depends on the order. It would be, I think, 0, 0, 0, 1, 2, something like this if this was reversed. The discussion would be the same, just with a different matrix, and it would square to this matrix. It's just a convention. Okay, so let me make one remark that, I mean, I've stressed before how similar matrices and transformations are, that matrices are basically just the blueprint version of a transformation, and that we can do everything with the transformation that we can also do with the matrix, and vice versa. So when you think about composition of transformations, so if you have T compose S, then this refers to multiplication A times B. So that's the composition in the matrix world. And because the first property here, the first item in the list, just says that matrix multiplication is associative. Remember that that was one of the vector space axioms for vectors. I'm not saying that this is a vector space. I'm just saying that because we have that composition of transformations is associative. So it doesn't matter whether we compose them in this order or in this order. This refers to the fact that matrix multiplication is also associative. And the important message that I'm trying to send here is that actually we haven't talked about this yet. I was kind of not realizing that this is this is part of the next section only. But the important story in this remark is that everything that you do for transformations can be done in some way for matrices. So just keep this in mind. And we're going to see this hopefully later, that we want to derive something from matrices, and I want to use what we had for transformations, because you don't have to invent the wheel every single time. One important thing that matrices and transformations have in common is that the dimension of the image, remember, that was the column space of the matrix representing a transformation. And so this number 4 is very interesting, because we can just define the rank of a matrix now, not in terms of the leading ones when it's row reduced, but we can actually just say that it has a column space. It's the span of the columns of A, and the rank is exactly that. This might actually be not a definition, but a proposition. But as a remark, I'm just saying that this is a fact, and you can prove this, or you can just remember it. Okay, so because the time is already so advanced, let me just say that this discussion is just to stress that AB equals BA is not true. So this is not. You can't change the order of multiplication of two matrices. And the reason is, again, in light of the remark, this will correspond to same with transformations, that T composed S is not necessarily S composed T. So it might not even make sense to compose them the other way, because if they go from U to V to W, then T composed S makes sense. So this can get a green check mark. But if you were to try to compose now S with T, then just S composed T doesn't even make sense. So just make sure that many things that you know from numbers generalize to matrices, but not commutativity. So this is not commutative. Any questions before we move to the new section? All right, so the new section, I would say there's just one essential idea that we add, and then we see how things behave to what we've done so far. So the only new ingredient is this first definition, and then everything else is just revisiting what we had. So we're going to revisit the propositions, we're going to revisit matrices compared to transformations, and so on. And since we have had composition, now we may ask a very special question. Is it possible to compose a transformation with another transformation so that it reverses whatever the transformation did? And this is just specified by an inverse. So if you compose T with S, remember that S composed T applied to a vector is S of T of V. And if this first condition is true, so I'm saying that if T is a transformation from V to W, and S is going the opposite way, so this is the opposite direction, you might even, you may want to write this as two arrows going from left to right. This is T, and then S is going the opposite way. So it's kind of working against it. It's going the opposite side. If you compose them, then it doesn't do anything to V. So this means in the above equation, at the above line, if I say S composed to T is equal to identity V, then this is just not doing anything to v. So it means that if you apply s after t, it undoes what t did. This is the first equation. The second equation is very similar. It says that if you do s first, so if you start with a w inside of the vector space w, and then we apply s, so we go over to this side, and then we go back to this side, then it's supposed to be the same as we started with, because there's an identity transformation, which we call w, id set w. And then this equation here literally just says that this is equivalent with saying that t composed with s of w, which is t of s of w, is supposed to be id of w, but this is just w. So if you have such an s to a given t, then we say that s is an inverse to t, and t, if it has an inverse, we call it invertible. So these are the two definitions I want to make in this first definition. I realize that this diagram on the right might be confusing, but I think it's important to distinguish whether you start on the right hand side, so you start with a w, or you start with a v. Are there any questions about this inverse? This is just a definition, and I think an inverse of a function is nothing new. So this is so far, I'm just saying that t is a transformation, a linear transformation, and I'm saying that this is what it means to have an inverse. Notice that I'm not saying that S is necessarily a linear transformation. I'm just saying it's inverse, not linear.
Just in general, I think we also have to check like both ways all the time, right? So it could be that we have like S composed T is the identity, but not the other way around. But we would have to check that just for it to be satisfied.
I could come up with an example where this is, yeah, exactly, yeah. It would have to be an infinite dimensional vector space in my example, but those examples exist. So it is important that you check both things. Yeah. Okay, so let's look at the proposition just to understand this a bit better, and then we're gonna see examples, I think. Yeah, so we're gonna look at examples very soon. I hope you stay with me. So the first one is, when does such an inverse exist? Like, what does it mean to have an inverse? And yes, so Idris asked in the chat, isomorphism, we defined this. Yeah, so this remark that we call bijective linear transformations an isomorphism. And if I prove this proposition number one, so if I prove this, then invertible is the same. This now is the same as invertible linear transformations by the first proposition. So this remark refers to the first proposition. We are equating two things that we've defined before, two different definitions, and now they're unified. So let's prove this first one. Well, if you suppose, let's go this way first. If you suppose that T is bijective, and we pick a W in the codomain, so in the target space, then what we want to do is we want to find it, we want to assign this, we want to basically construct. So the idea here is to construct S, the inverse. Then, well, because T is surjective, there is a V in V such that T of V is equal to W. This is just literally what surjectivity means. And then because T is also injective, the same V that we just, and the above line that we found that exists is the only element in V such that it maps to W. And so we just define, so W was arbitrary. So we could do this, we can play this game for every W in the target space. And so we define S of W to be V. So this side is not very mind-blowing, I would say. It's just we have some element that maps to W, and there's only one. So why not just pick this one to be S? It's not very this might be disappointing to see, but it works. So now we can verify indeed that if we have T composed S of any element W, so this is for W in W arbitrary, this is T of S of W, but this is exactly T of V such that V maps to W, so this is W. And similarly, S of T of V is S of T of V. But if we're given T of V and we apply this these two lines, these two constructions, we say there exists a V. Well, obviously V maps to T of V, but by injectivity, V is the only thing that maps to T of V, and so S is supposed to be that element. So this means this is supposed to be V. And so this means that T composed S is equal to the identity on W, and S composed T is the identity on V. Okay, so this concludes that if we have a bijective linear transformation, we can just construct the inverse explicitly. We can always just find the inverse. Let's do the opposite direction. Are there any questions about this? No, so Andrew just jumped ahead to the second point. If you could wait for 5 minutes, then I'm going to answer this. So we can't define it to be linear because we can't define things to have a property that doesn't work. We can define it to exist, or we can define it to be something, and then we can show it's linear. So it is implied. It follows from the inverse property. We can see this in a second, but that's a good question. Okay, so now we suppose T has an inverse S. Is T bijective? Okay, so this is just means we need to check whether it's surjective and injective. So if you pick any element in the target space, then we just apply S to it. Mean S of W in V is such that T maps it to W, simply because T of S of W is T composed S of W, and this is W. So for every element in W, there is an element that maps to it. I mean, that's the definition of surjective. And an injective, well, suppose that for V1 and V2 in V, T of V1 is equal to T of V2, and we know that it's an inverse, then this implies that S, that V1, which is equal to ID of V1, is equal to T composed, S composed T of V1. But now we use that T of V1 is equal to T of V2. So we can just replace, this is the assumption. So this starting point of injectivity, where we always try to show, we try to assume when we show injectivity, is exactly being used in this step. So this is S of T of V2, and this is V2, because S and T are inverses. So we've shown that if T, the value of T, the value under T of V1 and V2 is equal, then V1 and V2 have to be equal, just because there's an inverse. Yeah, this is a lot of theory. So maybe I'm gonna do the examples first, and then I'm gonna come back to the second point of this proposition, because I don't want to overload you with theory too much at one point. Any questions so far? But just remember that we've defined an isomorphism to be bijective, and we've now shown that bijective is the same as invertible. So then in total, we have now equated isomorphism, bijectivity, and invertibility. So that's now all the same by this proposition. Let's postpone the second part and look at examples, because then you might get a more feel for what an invertible transformation is. So actually, I want to start with the zeroth example, and I didn't include this because I didn't think about including it. So the zeroth example is just a vector space and the identity transformation IDV. This is, so ID sub V, which takes every vector to itself, is its own inverse. Because if you compose IDV with IDV, well, guess what? It is IDV. So it's kind of an extreme example, but it is nonetheless an example of an invertible transformation. Any questions to that? Then let's get to the first non-trivial example, the first real example. And I'm just going to draw something below these lines. So about the first one, if you have R2 and you have a vector on R2, then you can just rotate it by a third degree theta. It shouldn't change its length. So it's just being rotated. So this is V and this is R theta of V. And just literally take everything and just rotate it. And of course, if you rotate it back, but by the way, so I don't think we did this in class, but it's just good to know that R theta, the transformation of R theta. So if you have the matrix, the base is 1, 0, 0, 1, the standard basis of R2, then in this basis, the matrix representing this, this is not something that I can tell you without computation, because I mean, you can verify this. There's a way to prove this, but I don't want to prove this right now. This would be cosine theta minus sine theta, cosine theta, sine theta. And I mean, not algebraically, but just looking at this picture on the left-hand side, Oh, I didn't want to erase this. You can see that if you now apply a transformation that rotates everything back clockwise, not counterclockwise. So this first one was going counterclockwise. Then you can just see by this picture that our minus theta is rotating in the opposite direction. So this means r theta composed to r minus theta is equal to the identity operation on R2. If you rotate like a vase and then you rotate it back, you can't tell that it's been rotated. That's the idea. And interestingly, so what does this mean for the matrix side of things? So this means, just as an aside, this would mean that that cosine theta minus sine theta, cosine theta, which is one of the matrices, multiplied with the matrix of the opposite, with the opposite sign of theta, minus sine of minus theta, sine of minus theta, cosine of minus theta, would have to be equal to the matrix representing the identity transformation. But what is the matrix of the identity transformation? That would be just 1, 1 with zeros on the off diagonal. So this is equivalent in the on the matrix side to say this, and you can verify why this is actually true. And I could give you a hint that sine squared theta plus cosine squared theta is 1. Okay, but let's focus on the invertibility and not on other things. Getting distracted. Any questions? Aditya asked about, like, do you mean our theta? Yes, our theta, by the previous proposition, that's the reason that we went through all this this hustle and this work, is because we know now that invertibility is equivalent with bijectivity. I wouldn't, like, we didn't use anything that's homomorphic in this lecture. So homomorphism is something else that has nothing to do with invertibility. So please be careful with those words, because if we didn't define them, then they can very, very quickly lead to confusion. So, but Aditya's question is completely correct, that this map, or theta, has to be bijective. So if you rotate something, and if you rotate another thing and they're equal rotated, they had to be equal to begin with. So you can rotate two things that become equal, which weren't equal before. No, Andrew, homomorphic doesn't imply isomorphic. We can talk about some office hours. I have office hours in exactly 20 minutes. Okay, let's go through these examples. I'm terribly slow today, and I'm sorry. I don't know why. Maybe it's a good thing. So there's two more examples. So let's look at the second example. The second example here is the evaluation map of a polynomial evaluating at the point 4. So why can't this have an inverse? Well, it's not injective. So we saw last time that if we have a polynomial, so this is say this is R2, and this is how do we draw this best then? So these are just different these are just different polynomials. So this is P of X, Q of X, and R of X. And let's say that that this point here, where they're supposed to agree, this is 4, then the then this value is exactly, so Q, the evaluation at 4 of Q of X is just giving us the number Q of 4. And we can see that just by drawing this, I mean, you can have polynomials as wild as you want. So from this drawing, you might have to explain this a bit further if this was a test. I'm just saying that you can get the idea, the intuitive idea of this from this picture, that the evaluation at 4 of Q equal to the evaluation at 4 of P means that Q of 4 is equal to P of 4. So these polynomials intersect P and Q at x equals 4. But this doesn't mean P equals to Q. As we can see, it may mean that P is not equal to Q, as in this case, I've drawn 2 different polynomials. So this means the evaluation map from polynomials to real numbers is not injective. And then by proposition, can't be invertible. So there's no way that you can actually invert this map and get back a polynomial just by knowing its value at 4. And the last one, and any questions about this example? Okay, so the last one is a projection, and I didn't define this before, but maybe we can just use the last 5 minutes to look at this. So let me draw a picture for this first, and then I'm gonna explain this with math. So if we have a vector, say x, and we have a vector y, then inside of R2, I guess you've learned this in 223 other courses, you have this dot product. We have x dot y, which is equal to x1, y1, and so on, xn, yn. And we also define that x dot x, which is just the same thing, which is x1 squared, xn squared. This is supposed to be the length of x, only that we squared. So the square root of these squares will be the length of x. This is kind of the notion of length. I'm not going to go into much detail about this. It's just something that we can use to define interesting transformations. Because the projection of y onto x, this is what this is called. This is the proj sub x is the projection onto x, and we apply this to the vector y. So this is a linear transformation for any fixed x. So the idea is that you can actually define Rn to Rn, and you can just define proj sub x. And for every y, you just apply the projection onto x. And I guess an exercise is show that this is linear. It's just a homework that's not compulsory. Just if you're interested, think about this. So this projection is defined to be the dot product of x and y divided by the length squared of x. And then this whole thing is going to be a scalar. And then we just scale the vector x with this scalar. So this is it's going to be a scalar. And this is scalar multiplication. So the idea behind this, the reason that this is interesting is because when you draw these vectors in R2 or Rn in general, then the result is just going to be the shadow of a vector onto another shadow, another vector. So you can think about this as the shadow that y would cast if there was a light shining onto x. So if there was a light source of some kind, then this would be exactly the projection of y onto x. It depends on what kind of dot product you use. I'm just saying that we use the standard dot product in R2. And now the question is, why is this not invertible? Well, similar to before, if you have two different vectors, they might project to the same thing. So you might have different vector that's here, and it might also be projecting to the same thing. So this might be the vector z. So then the reason that projection onto x is not invertible simply because it is not projective. And you can also see that if you had this black vector, say this is, we can call this projection x of y, which is the projection onto x of z. If you wanted to find an inverse, so finding an inverse to projection x is not possible. I don't know how to write this, but you'd have to decide where to put this vector. And you have to, if you apply the composition of this inverse with t to y, it has to go back to y. But if you would apply the composition of the inverse with the projection to z, it has to go back to z. So you can't decide where to put this inverse, whether here or anywhere else. Okay, so I think the time is up. I don't think it's responsible to now go on and talk about the second part here, but I'm just gonna leave it at this. I'm kind of surprised that I've in the examples where I wanted to talk about invertible transformations, half of the examples are not invertible. I don't know if that's helpful or not. If you want more invertible transformations, just tell me and maybe we could come up with more. Yes, exactly. So Aditya had a good point. You can think about so maybe let's make a remark here. So any vector that is perpendicular And I'm not defining exactly what perpendicular means in this case. So any vector like this, let's call this u. I think what usually we call them, like, yeah, let's call them just orthogonal vectors. Orthogonal vectors u to x. Well, I can make this precise. I.e. vectors with dot product between x and u is equal to 0 will be in the kernel of the projection onto x. And this is non-trivial, so it's non-injective. That's a good point. Thanks for pointing that out. Yes, Idris also wrote in the last messages that this is exactly the null space, the kernel of this projection, and because this is non-trivial, this can't be invertible. I guess that's just a useful thing to know. So I don't regret spending too much time on this, but tomorrow we'll move on. Any other questions?
Hi, Professor. So I just it's from earlier. So I'm just wondering what's the difference between homomorphic and isomorphic? Doesn't homomorphic mean that the image is the same as the domain?
Okay, so let me then end the recording the lecture here, and I'm going to continue with my office hours from now on. So everyone else who doesn't want to go to my office hours is now free to go. I just like have a clean cut between office hours and the lecture.